आज के today's topic is magnetism and magnetic property of the material. Okay, so first I'm going to discuss about a bar magnet. Bar magnet. A bar magnet is such that it has two magnetic pole. One is north pole, another is south pole. Suppose M is pole strength, either north pole or south pole. Pole strength either north pole or south pole. Both have the same pole strength M, and if the separation between north and south pole is L, then this bar magnet associated with a certain parameter that is called magnetic dipole moment. Magnetic dipole moment. Okay, so that magnetic dipole moment, in some books it is defined or denoted by PM, or in some other book it is denoted by capital M. So magnetic dipole moment, either PM or M, let's consider it as M, is nothing but M into L. That means pole strength into separation between the poles, M into L, and its unit is ampere meter square. Okay, in SI. So this is our magnetic dipole moment. It's a vector quantity and it is always directed. M is a vector. M is a vector quantity and it is always directed from south to north pole. That is, M is from south to north. Okay, just to compare it with the electric dipole, say this is a minus Q charge, this is a plus Q charge, the separation is L, so it also forms electric dipole, and that dipole moment P is given by charge into separation, similar, and this dipole moment also is a vector quantity, electric dipole moment, and it is directed from minus Q to plus Q. Okay, the same thing. So S pole is equivalent to minus charge and N pole is equivalent to positive charge, and that's why its magnetic dipole moment is directed from S to N. Okay, now some more important qualities or properties of bar magnet. So already we have. So for a bar magnet, suppose this is a bar magnet. This is a bar magnet from N and S. So from north pole, magnetic lines of force coming out. Okay, magnetic lines of force coming out, and to the south pole, magnetic lines of force enter. That means magnetic lines of force coming out from north pole and enter into the south pole. Lines of force coming out from the north pole and enter into the south pole. Okay, and also if there are some other lines of force there, then that lines of force, that means other magnetic lines of force originate from other sources, that magnetic lines of force also enter into the south pole. And here lines of force originate from north pole. So the main property is that the magnetic lines of force originate from the north pole and it enters in the south pole. So outside the magnet, lines of force coming out from the north pole and enter into the south pole, but inside the magnet, lines of force coming out from the south pole and end at north pole. So magnetic lines of force is a closed loop. Outside the material, outside the magnet, it comes out from the north pole, enter into the south pole, and inside the material it comes from south pole and ends at north pole. So it's a closed loop. Okay, So magnetic lines of force is a very important property. Magnetic lines of force, is a closed loop. Why so? Because as I have told you, these lines of force coming out from the North Pole and on the South Pole, also the material, but inside the magnet comes from the South Pole and end at North Pole. So this is our basic idea of the magnetic lines of force. Okay. So this is a very important property that outside the magnetic lines of force comes from north and south, and inside the magnet it comes from south and end at north pole. Okay, this is the number one property. Next I'm going to next property is number two. Next property number two. So at any point, if there is a magnetic field, if there is actually what happened when you place this bar magnet over here, then surrounding medium get magnetized, or surrounding medium, not magnetized, surrounding medium, a field is developed in the surrounding medium. A field is developed, and that field is called the magnetic field. Okay, magnetic field, and you can say that magnetic field is developed by this bar magnet. Okay, so the existence of the magnetic field is now represented by the magnetic lines of force. So if there is a magnetic field, then obviously there should be magnetic lines of force. So existence of magnetic field is represented by magnetic lines of force. So we consider that this region is a region where magnetic field exists. So this is a region where magnetic field exists. That means this region is represented by the magnetic lines of force. Okay, this is the magnetic lines of force. Okay, these are the magnetic lines of force, say. Okay, and one thing you have to just you consider or imagine that at this region, at this surrounding this point, there are few lines of force, but surrounding this point, the number of lines of force is decreased. That means if you compare between the points A and B, so A have more lines of force. A have more lines of force density. That means number of lines of force per unit area surrounding the point A is greater than the lines of force, magnetic lines of force surrounding the point B per unit area. Okay, that means you can say that in terms of lines of force at the point A, magnetic field strength is higher than the point B. So magnetic field strength or magnetic field is higher at A than B. So this is one more important point to understand. Okay, number 3 point is if there is a magnetic lines of force. Okay, suppose this is a magnetic lines of force. So at any point, suppose at that point the direction of the magnetic field, just draw the tangent. This tangent gives you the direction of the magnetic field at the point, this point. So if you want to find the magnetic field direction at this point, then draw a tangent over here. You got a magnetic field direction at this point. So at any tangent on the magnetic lines of force gives you the direction of the magnetic field at that point. Okay. So conclusion of this property 3 is suppose if we have this kind of magnetic lines of force, that means this is 1, this is 2. So and these two magnetic lines of force intersect each other at the point at this point, and this could not be happen. Why so? because if you draw a tangent at the point at this point for the curve 2, you will get this is the tangent on the curve 2, and this is the tangent on the curve 1. And you see at the point P you have two tangents. That means at the point P you have two magnetic lines of two direction of the magnetic field, and at a particular point two direction of the magnetic field is not possible. So at this point this is not possible that at any particular point the magnetic field has two directions. So from this understanding you can easily conclude that magnetic lines of force never intersect each other. So magnetic lines of force never intersect each other. Lines of force never intersect each other. Never intersect with each other. Okay. So this is a very important conclusion. So okay. So what we have studied till now, there is a bar magnet. Okay, so a bar magnet have two magnetic pole. One is north pole, another is south pole. Okay, each pole has a magnetic pole strength M. M is represented as a magnetic pole strength, small m. So pole strength as a north pole or south pole, because each pole have the same pole strength. Okay, so since it's a magnetic dipole, because there is a two pole associated having separation L. So every bar magnet or magnetic dipole has a dipole moment. This is called magnetic dipole moment. Can be either represented either by PM or by capital M. Let's for simplicity we will consider it as PM. M. M is nothing but magnetic pole strength into separation between the pole, M into L, and this unit is ampere meter square. Later I will discuss why this unit is ampere meter square. Okay. Until now you just mark up this formula. M is a vector quantity, and you should remember that M is a vector quantity, and the direction of the M is always from south to north. Okay. Just compare it with a electric dipole. So in electric dipole we have two charge. One is positive charge, another is negative charge, -2 +2, having separation L. So this combination is also called electric dipole, and it is associated with the electric dipole moment P, and that P is given by charge into separation Q into L. So this is a electric dipole, and also this electric dipole is a vector quantity, and it is always directed from -Q to +Q. Okay, so these are the similarity between magnetic dipole and electric dipole. So from that discussion we can conclude that the south pole is equivalent to magnetic electric negative charge, and the north pole is equivalent to our electric positive charge. Okay. Since we placed a magnetic bar magnet, it has north pole, south pole. So from north pole we have already have our this concept that from north pole magnetic lines is coming out and it ends at south pole. Okay, but inside the material the lines of force coming from the south pole and ends at the north pole. So from that discussion we can conclude that magnetic lines of force is a closed loop, because outside the material it is coming from the north pole and ends on the south pole, and inside the material it is coming from south pole and ends on north pole. So magnetic lines of force is a closed loop. Okay, and this is actually not for electric dipole. Electric dipole is not a closed loop, because electric dipole only originate from the positive charge and ends on negative charge. So these are the electric dipole. Okay, and this is not possible that inside this -Q to +Q, only outside. Electric lines of force exist only outside the electric dipole. For magnetic lines of force outside the magnet is from north to south, but inside the magnet is from south to north. So it forms a closed loop. Okay. Another thing is that when you place a magnet in this space, surrounding this magnet, magnetic field produced, and magnetic field existence of the magnetic field is represented by magnetic lines of force. Okay, existence of magnetic field is represented by magnetic lines of force. Okay, let's suppose this space is a magnetic field. This space has a magnetic field, so we have some magnetic lines of force. Some magnetic lines of force looks as I have drawn over here. These are the magnetic lines of force. That means this space is have some magnetic field. Okay, if you observe very minutely surrounding the point A and surrounding the region point B, so this region have a few more lines of force, but this region have a very less lines of force. That means okay, that means you can say that surrounding the point A have a higher lines of force and density than surrounding the point B. That means A point have a higher lines of force density compared to point B. That means at the point A, magnetic field strength is higher than at the point B. Why? Because now we have another point. That means that is higher the lines of force density surrounding a point is corresponds to higher magnetic field strength or higher magnetic field vector. Okay. So magnetic field strength means H, magnetic field vector means B0 in free space or B in any other medium. Okay. So higher the magnetic lines of force at any point, higher the number of, if at any point number of magnetic lines of force is higher, then that means that point corresponds to higher magnetic field strength. Okay. Another important point is that suppose this is arbitrary magnetic lines of force. Okay, so at that point your magnetic field strength is directed tangentially. That means if you want to find the direction of the magnetic lines of force, or if you want to find the direction of the magnetic field, you have to draw the tangent at that point on the magnetic lines of force. So at that point this is the tangent, so this is our magnetic field direction. At this point this is our tangent, so this is our magnetic field direction. If you draw tangent over here, so this is the magnetic field direction. Okay, and another point is that magnetic lines of force never intersect each other, because suppose for some reason, suppose this 1 and 2 intersect at the point B, then you can draw two tangent at the point B. One tangent over the first lines of force, and second tangent over this number 2 lines of force. Okay, so this two green color tangents shown at the point B. So these two tangent gives two direction. So at the point B we have two direction of the magnetic field if the lines of force intersect at the point B. So that means lines of force never intersect each other. So this is the very important understanding you have to mark up, or you have to understand. Okay, next I'll do some other thing in the next video.